What's up, guys? Today I wanted to talk about solving for the internal loadings in a member. So the way we do this is that we section the member at a point and then we evaluate those internal loadings on either the right or left side of the member where we section it. So in this case we're asked to section it at point B. So we'll section it at point B and then we'll evaluate those internal loadings that are present. So we're still going to have a distributed load here, but it's not going to be the original 60 pounds per foot. It's going to be less. So in order to calculate what that's going to be, we'll use the law of similar triangles, and we'll say that our weight over our new distance, which is 12 feet, equals the original distributed load over the original distance, which is 15 feet. And when we solve for that, we'll get that W equals 48 pounds per foot. So let's draw this. I forgot to draw the total distance of the member here. This is 12 feet. So we'll have some internal loadings going on here. And initially, we're just going to solve for the three basic ones: normal force, shear force, and the internal moment. Later on, we'll have some other forces in there, but we're not worried about that for now. So we'll do the normal force here, N sub B, the shear force, V sub B, and the internal moment, M sub B. And the way this works is the convention for moments and shear is that if you've got a moment that rotates, if you've got a moment that bends it like this, it's positive. And then if you've got a moment that bends it the other way, it's a negative. And the way I like to think about it is that when it basically bends it so that it creates a smiley face, it's positive, and if it bends it so that it makes a sad face, then it's negative. That's for the moment. For the shear force, the convention is just that if it tends to rotate the beam in a clockwise direction, then it's positive. And then obviously if it rotates in a counterclockwise direction, it's negative. So we always draw these internal loadings so that they're positive. The shear in the moment. So now we need to solve. Well, let's go ahead and solve this resultant force, and we know it's going to act a third of the distance from this fat side, so that's 4 feet. So what's that resultant loading? It's going to be, we say 1/2 BH. So in this case, it's 1/2 of the base is 12 feet. And this distributed load we said was 48 pounds per foot, which comes out to be 288 pounds. So that's our resultant force acting here. So now we're ready to take some of the forces in the Y, some of the forces in the X, and some of the moments to get our internal loadings. So you might be able to tell right away that some of the forces in the X, this internal normal force is the only force acting in the X direction. So when we take some of the forces in the X equal to 0, the right will be positive, we'll just get negative NB equals 0. So that tells us that the normal force, the internal normal force, is equal to 0. So for the shear force, we've got, well, we'll take the sum of the forces in the Y direction equal to 0. Up will be positive. So we've got a positive VB minus our 288 pounds equals 0. So from that, we'll be able to tell that our internal shear force is equal to 288 pounds. And lastly, our internal moment, which is going this way. So if we take a sum of the moments about point B equal to 0, we'll call counterclockwise positive because that's usually the convention. So we've got, in this case, a negative MB, negative MB minus 288 pounds times a moment arm of 4 feet equal to 0. And when we solve for that, we'll get that the moment MB is equal to negative 1,152 pound-feet, which is equal to negative 1.152 kip-feet. And that's it. So the big things are going to be section it at a point that's convenient. A lot of times it'll tell you where to section it. And then use whichever side will be easier. In this case, the right side was easier, more convenient, just because it left us with a nice triangle. And then remember to follow these conventions for the, for the moment and the shear force. And solving the forces is relatively straightforward. For the most part, your normal force oftentimes is going to just come out to be 0 because your support force will be the only force in the x direction. So that's it. I hope you guys enjoyed the video.